It's this will be we can start.
Yeah. So, hello everyone. First of all, thank you for joining us in this online summer school session, which is being offered by Horizon today. So, I am V. Thiruselvi, and I am here along with my friend Gautaman, and we are going to take you on a journey through the stellar evolution. Okay, journey it sounds dramatic, right? But still, you can have a look around you, or maybe at your own body. The iron in your blood, the calcium in our bones, the carbon in our DNA. Like they didn't just appear out of nowhere, right? They were, in fact, forged billions of years ago in the cores of the dying stars. And that's why the legendary astrophysicist Carl Sagan once quoted that we are made of star stuff. That is, basically, we are stardust. So today we will be showing you exactly how this cosmic stuff is being forged inside the cores, and we will also be revealing the dramatic future which is awaiting our very own sun, and much more else. So stay tuned till the end of the session. Okay, now let's take a quick look at an overview before we begin the so-called cosmic tour. So first is you will be exploring different stages of the stellar evolution, like what forms the star is going to exist as and all. And next you will be understanding what the role of a mass of the star is throughout this life cycle. And thirdly, you will be learning the fundamental physical principles which govern this whole stellar evolution process. And finally, we will also be discovering some intriguing facts about the star and their role in shaping the universe. This life cycle it splits into three completely different pathways, but that it completely depends on how much material star is going to scoop up from its molecular cloud. Now, that is the main takeaway which I want you to understand from here. That is, the star's initial mass at its birth is what is going to dictate its entire journey, this entire life cycle. But irrespective of its initial mass, every star's journey they begin within the most beautiful gigantic structures, which we often call as nebulas. So, what are they? Let's take a brief look at them. So, to define nebula, they are nothing but some colossal cloud of dust and gases, which can span about like millions of light years across. They are very gigantic. And they are also nicknamed as nursery of stars because they provide the necessary raw materials and the protective environment for a baby star, to form and grow. That's why. And I hope you can see this image here, right? So this was one of the most beautiful image which was captured by NASA's James Webb Telescope. Here it is showing a nebula called Carina Nebula, which is often called as cosmic cliffs because of its structure. Now, as you can see, the brown dense regions, right? So those regions are nothing but the places where the intense star formation process takes place. Now, by seeing them, you might think that they look very thick and dense, meaning they'll be having high density and all. But actually, their density, like they are really incredibly empty. That is, they have a density of only about 100 to 10,000 particles per cubic centimeter. Now, if I compare it with something like, for example, let's take some of the well-built vacuum chambers which we have on Earth, and when we compare them, actually it is noticed that these nebulas are far more emptier compared to those vacuum chambers which we have on Earth. So I guess you can understand, right? But that raises a very important question that for intense formation, like intense process like the star formation, we need to get these particles to come together and increase their gravity and all that. Then that means nature here it might need a very violent trigger. So that trigger it or spark it usually comes from one of the two massive galactic events, which are the collision of giant nebulas and the supernova explosion. What happens when two nebula collide is they come together and they form certain high density areas, like high density lump of gases. And when supernova occurs, usually it sends out shock waves, which when it ripples through the structure, it will create some kind of sudden density fluctuations. So as a result, certain regions it will become denser, it will become highly dense. Now, once the gas transforms into a high dense pockets of gases, the cloud's own gravity will try to collapse it very further. Now, it is not alone here. It will start a tug of war with another force, which is the thermal pressure caused by the gas particles. Now, who is going to win this tug of war is like whether the gravity will win or not is completely determined by the cosmic boundary set by what is called as gene stability. Now, this gene stability, it can be expressed in terms of mass or length or time. But here, let's take a look at through the lens of time, where we be comparing to competing clock cycles. So for that, you have to know what are these two terms, that is TSC, TFS. Now, if you imagine those shock waves or pressure waves as a sound wave, the time it takes for that wave to travel across this gas cloud is nothing but TSC. And TFF is the time, is also called gene time or free fall time, is basically the time it takes for the cloud to collapse under its own gravity. So it is given by the formula which I have shown here. Now you have to understand this time is inversely proportional to the rate at which these both pressures try to dominate. Meaning when this gas cloud satisfies this equation TSA greater than TFF, it basically means that gravity here it will contract the system way faster than the pressure forces can actually resist. So as a result, the gravity will win the tug of war and it will try to dominate. As a result of which, this cloud it will undergo a runaway gravitational collapse. Now, this as a result of this collapse, this cold patch of gas it will evolve into a glowing infant object, which we call as protostar. Now, okay, and the protostar is the next stage in the evolution cycle. Now, let's take a look at what happens inside this protostar. Now, protostar, they are also called as stellar embryos. Why so is because they are the infant star who hasn't still, begun their hydrogen fusion reactions. Still, their temperature aren't that high enough. So that brings us to one characteristic which I have stated here. That is, this protostar, it generates heat through gravitational contraction rather than nuclear fusion. That's the first thing. And second, for that, that is completely explained by this picture which I have here. Now, this is also one of the beautiful pictures which was captured by James Webb Telescope, which shows a protostar which is growing by feeding on its parent molecular cloud, which is called as 11L1527. Now, this is how a protostar grows. Like it constantly pulls in the surrounding material from its parent molecular cloud. And that explains the second point. And third is they also produce powerful winds and bipolar jets, which often erupt from their poles, like magnetic poles. Now, it isn't always a guarantee that this protostar will evolve out to become a developed star, which has began its fusion and all. Its fate will completely depend upon who is going to win the tug of war here. Now, the tug of war is between the gravitational pressure, which is trying to collapse it, and another force, which is brought down by the quantum laws, which are called electron degeneracy pressure. Now, as a result of this tug of war, the nature will draw a very strict line here at the mass limit of zero point 0 m, sorry, 0.08 m. M here is nothing but one solar mass, which is equivalent to the mass of our sun. So, mass of any celestial being we actually calculate with respect to our sun. Now, once this protostar, if it is greater than this mass limit, then it will become a developed star called main sequence star. But in case if it is less than this limit, then it will become a failed star. It will fail to ignite its hydrogen fusion reaction, and it will become what is called as brown dwarf. Now that makes us wonder what this quantum pressure is, right? Now, yeah, let me detail about what this pressure is and how we get it and try to make sure you try to grasp this concept because you'll be dealing with this throughout this session, like other forms of it. And okay, coming down to electron degeneracy pressure, you can take a look at its definition. So it is basically a non-thermal quantum mechanical pressure exerted by highly dense gas of electrons. So quantum mechanical, okay, it's understood that it is caused by quantum laws. Why it is called non-thermal is because it is completely independent of its temperature. Then what it depends on is completely about how confined the matter is. Basically, the density of the protostar. Now, till now we were dealing with the normal thermal pressures, right? Then how did a star transition from that thermal pressure thing to this quantum pressure? Like you might wonder, right? So it all starts again with this gravitational collapse. So what happens is under that immense gravitational squeezing, the individual atoms in the matter they are forced to get so close to each other that their energy levels will start overlapping. That is, they merge into form a continuous series of energy bands, which was very similar to what we see in case of semiconductors. Like I hope you remember those concepts. So, and those electrons, they get ripped apart from their atoms, individual atoms, and they get squeezed to form an ultra dense sea of electrons. And they start arranging themselves like randomly in that energy bands. So this whole arrangement is shown in this first figure. Like you can see, right, the electrons are randomly arranged. Right now, the density is not very high, so they are occupying this any sort of place which they find there. Now, actually, this quantum state, which I'm mentioning here, is nothing but those each individual boxes which we have. So each box they represent a quantum state. Now, okay. Now, once this gravity cranks up this matter to and causes the density to hit some extreme levels, at a particular density, it actually triggers two fundamental rules of the quantum mechanics, which are the Pauli's exclusion principle and the Heisenberg's uncertainty principle. Let me state that, though you have already studied them, let me state what they are. So, first, Pauli's exclusion principle, it states that no two identical electrons can occupy the same quantum state, which are those individual boxes here. So, if I want to explain what is the impact of this principle on this behavior, is maybe you can try to imagine this whole setup like a giant theater, where each row, like each rows are represented nothing but energy levels. Now, what happens is these electrons they first arrange themselves in the lower energy order because as a result of that they will be very stable. So yeah, they occupy the ground level and then first energy level and second energy level. Like that, they occupy all the lower energy levels, which are more like a front row seats in a giant theater. And then the remaining electrons which we have here, they are completely forbidden from going there according to this principle. So as a result, they have no choice and they start to occupy the higher rows, which are nothing but the higher energy levels. Now you have to understand that this isn't because of the typical electrostatic repulsion. It is a strict law of this quantum bookkeeper. So that's the main point to remember. And this is where the second principle, the Heisenberg principle, will come. That is, here the electrons are being squeezed into tiny volumes of space, right? So that causes their position to become more certain. That is, the delta x value will go towards zero, causing the delta p value to skyrocket, meaning now it will become more uncertain, the momentum. So to satisfy this law, what will happen is the electrons in the higher energy levels, they are forced to move around or zip around under like in some immense speeds, like incredibly high speeds. It is this kinetic energy of those speeding electrons which will create a massive outward pressure that we call as electron degeneracy pressure. Now, if you are wondering, like we were talking about energy, right? Now, how we mapped it to the pressure, if you ever have that doubt, then you have to understand that pressure can also be written as energy per unit volume. That is basically, it can be expressed as energy density. Now, one of the implications of this pressure is once this EDP comes into picture, it will basically lock the core. Meaning now the core can neither expand nor contract under any circumstance, and that we call as quantum equilibrium. Now, okay, now let's take a quick look at the how the derivation, like how what is the equation of EDP. Now it is derived from that thing which I said earlier, P is equal to dE by dV. Now from there, if when we plug in some quantum formulas, we end up getting this huge equation. Now don't focus there, remember. The only thing I want you to focus here is this final equation. That is, P is directly proportional to density power 5 by 3. So this is this non-relativistic EDP equation. Now, if you wonder what non-relativistic is, then it is the region where we deal with particles which are moving in speeds that are very less compared to the speed of light. If we deal with near light speed particles and like those kind of speeds, then what we call it relativistic region, where all relativity laws and all will come. But here we assume it's non-relativistic. Now, okay, let's contrast this with another equation which we have here, which is the inward pressure exerted by the gravity. It is derived from this equation which we have here, dP by dr is equal to the Newtonian gravity. So this is the equation of equilibrium. I will explain it in a while. Don't worry. What I wanted to focus here is this P gravity is proportional to mass power 2 by 3 and density power 4 by 3. Now, if you closely compare them and look at their exponent, you will find that EDP's exponent is higher than GP's rate. Meaning now, if we increase this density by the same amount, the EDP will grow faster and it will try to dominate the gravitational pressure. But if you notice another factor here, that is M, the GP is also dependent on M, right? So if this mass M value is beyond certain limit, then it can also dominate this EDP and it can produce higher temperatures and it can ignite this hydrogen fusion process. And that limit is what we call as the zero point zero 0.08 limit. So basically, we obtain that by equating these both. Now, okay, now let's assume the protostar is greater than zero point zero 0.08. Then what happens is now the gravitational pressure will dominate this EDP, and it will easily crush the core and will start igniting the hydrogen fusion reaction. Way before this EDP can reach the density and it can take over. So that's how a true star is born. But if this protostar mass is less than 0.08, according to what we saw here, according to this logic, the EDP will ramp up and it will dominate this gravity. So as a result, what happens is the core will become electron degenerate, meaning when this degenerate pressure comes, it actually locks the core in place, right? So the core can neither contract or expand now under any circumstance. So as a result, the core will get locked before it can even attain the hydrogen fusion temperature, which is 4 million Kelvin. So basically here the gravitational heating has stopped that the core now it will never get any hotter and it permanently prevents the fusion reaction from occurring. So this leaves us with what is called as brown dwarfs. And as you note here, actually you can find the Jupiter here, right? Now Jupiter also has shared the same fate as brown dwarf because if you compare its then its mass is actually 80 earning a spot on one of the grandest map which we have in astrophysics. That is nothing but HR diagram, also called as Hertzsprung-Russell diagram. So it is nicknamed as periodic table of stars. Now let's see what they are. To define them, they are nothing but a scatter plot which will map the stars based on their inherent physical properties like luminosity or surface temperature. Now, on the y-axis, what you have is the luminosity, which is often measured related to the sun's luminosity. And on x-axis, we plot the surface temperature, which is measured in Kelvin. Now, there is a very big catch here, which is that x-axis, if you observe, it is completely backward, meaning the temperature is actually decreasing from 30,000 to 3,000 here. So that is a major thing. Now, if you try to compare these temperatures to that spectral scale, which we have there, then I guess you can understand that blue colors often denote the hottest temperatures, like in the blue jeans. But the red colors of the star, they often show that their surface temperature are far less, like 3,000 Kelvin. They represent low temperatures. Now, if when you collect all the stars' properties like these values, and when you try to plot them here, they actually seem to sort themselves into some distinct neighborhoods based on which stage they are in. One minute. Sorry for that. Fine. So let me briefly say what are the regions you find here. So first is the white dwarf region, which you can find in the bottom left. On the top right, what you have is some supergiants and giants, which are very massive enough. And on the center, on the diagonal line, what you have is the main sequence diagonal line, where you are having all the main sequence stars. And if you take a close look at them, actually at the top left, you can find there are we have the highly luminescent blue giants, whereas on the bottom right we have red dwarfs, which often have surface temperatures that are double times lesser than a typical sun surface temperature. Now, if you closely look at that red dwarf region, I guess you can find one of the well-known stars, which is Proxima Centauri. Proxima Centauri is actually one of the closest star. Yeah, it is the closest star to our sun, and it's basically a red dwarf, which makes it the smaller than sun, and also it has very less surface temperature compared to sun. Now, okay, so that's about the HR diagram. Now let's take a look at one of the most populated highways, nothing but the main sequence diagonal line. So on this diagonal line, you have what is called as main sequence stars. They are also known as core hydrogen burning stars because they have officially started igniting their hydrogen into helium. That's why they are called like that. Now, one of the main characteristic is their duration. That is the duration which they spend on this particular stage. It is completely dependent on their mass. Meaning, for example, if you take the low to intermediate main sequence stars, their main sequence life often goes like hundreds of millions of years to hundreds of billions of years even. But when we talk about massive, like the blue giants which we had there, their life will be more like some 3 to 30 million years, only that short period. Why do we have this difference is because if a star is very massive, which that means it can provide more crushing gravitational forces. So that will actually cause the fusion rates to be very higher, and as a result, it will start consuming its fuel much more faster, and that's why massive stars they live for a short period. Now the next characteristic is this is the most stable period in a star's life at all. Why so? It's because of this equilibrium called hydrostatic equilibrium. Now, if you wonder what this equilibrium is, then it is nothing but when the star's primary forces, like this outward thermal pressure and the inward gravitational pull, when they balance out each other, then it is said to attain an equilibrium, which is called as hydrostatic equilibrium. Now, this balance it applies to every single layer of the star. Like if you divide the star into several layers, we can apply for each single of them. So, so you can take a elementary shell here, and when you try to balance out the equation, you will end up with the stellar hydrostatic equilibrium equation. So this is what we dealt in the EDP section, right? So this next slide, what we have is the pressure gradient across that elementary layer which we took, and on the right side, what we have is the Newtonian gravity, which is the inward pull on that layer. Now we have the negative sign here because they are opposing each other. That's why. Okay. So this explains the equilibrium. Now let's move on to the nuclear engine, which keeps this star alive, actually. So what keeps it alive is this hydrogen fusion process, where hydrogen gets fused to helium. Now this can happen through two ways, two chain reactions. That is first this proton-proton chain reaction, and next the CNO chain reaction. But when you take a low mass stars like our sun, their core temperatures will be far less than like 16 million Kelvin. So for them, usually the proton-proton chain reaction will dominate. Now, yeah, let us take a deep look at what this reaction is. So as you can see from the picture, I guess you can understand this is a more like a linear step-by-step building process. First, what we have is the two individual protons. They will smash together to give out deuterium. Now, the deuterium will quickly smash onto a third proton, giving out a helium-3 nucleus. Now, it actually collides with another helium nuclei, which you can find in its surrounding, and it will blast out to give two protons, which leaves behind a helium-4 nucleus. And this is how the hydrogen conversion to helium takes place in this chain reaction. Now, that is one of the cool fact about this chain reaction. That is, this fusion reaction is very, very slow. And if you have noticed them, you would have already found it that some half times are like 10 power 9 years and 10 power 6 years. Why we have that much long period is because of this quantum bottleneck. Let me explain what it is. So, if you take the first step, that is when the two protons collide, they end up forming a very unstable nuclei, which is called as helium-2. Now here, the electrostatic repulsion between them is so high that it cannot be overcome by their strong nuclear forces. So as a result, what happens is within some 10 power minus 21 seconds, these two electrons will almost fly apart from each other. So by considering this, when try to calculate the probability of a successful reaction, it will come out to be the staggering one successful reaction out of 10 power 26 attempts. That's such a less probability, right? And that extreme quantum delay is also one of the reason why stars like our sun they can live for peacefully for billions of years instead of exploding out like a giant bomb all at once. Basically, it's a blessing in disguise at this point. Now, if you talk about massive stars, they really don't have time for the slow process. So because their limit, it is actually even like 1.3 times greater than our sun. So as a result, their core temperature will easily cross that 16 million Kelvin mark. So as a result, we have another aggressive engine which will take over. That is nothing but CNO cycle mechanism. So it is not a linear process. Instead, we have a six-step catalytic loop here, where the hydrogen will get fused to helium, having carbon, nitrogen, oxygen as the catalyst. Now let's take a quick look at the reactions. This is how the reactions proceed, like the sixth step. Now, the protons, instead of waiting for another proton here, this proton will directly smash into some existing carbon 12 which it can find. And thus it will form this cyclic loop, which will end up, capturing almost a total of four protons. And it will undergo some successive decays, to which will finally give out this helium. If you observe this last reaction, we have carbon 12 also along with helium, right? Now, the same carbon 12 will again get used in this first step, and that's why we actually it ends up becoming a closed loop. Now the thing about this carbon, nitrogen, oxygen is they were actually not formed in the star. They were actually created by the dead stars which lived long ago. So these are basically remnants of left by those dead stars. So they got embedded into that parent nebula, and that's how they became the part of the star. Don't misunderstand, like they actually got fused along with the hydrogen and all. Now, there is another thing which makes this very remarkable cycle, that its reaction rate is highly sensitive to the temperature. That is, if you try to increase the temperature by the same amount, the CNO's energy output now it will explode very aggressively and more highly compared to the proton-proton chain output. So as a result, this CNO chain will actually dominate, and that's how we have very less periods of life for massive stars. Okay, now that concludes the nuclear reactions. Now let's try to fast forward the star's main sequence life. So we basically reach the end, right? Now that brings us to this ultimate stellar boundary line in the cosmos, which is called the 8 solar mass limit. Just like the 0.08 limit, which I explained there, this line will strictly divide this whole universe into the group of low to intermediate mass stars and the massive stars. Now, if you stand on this line, like, okay, let's try to see how the stars below this line are going to evolve. So, for that, I will pass the lead to my friend Gautam. So, he will be explaining how the low mass stars evolution is going to look like. Yeah.
Okay, thank you, Thiruselvi. Hi guys, Gautaman here. So yeah, I'll be taking over from now on. So okay, let's get started. Okay, fine. So far we have followed the journey of a star from its birth. We saw how a star forms inside a nebula and how it becomes a protostar, and then how it spends most of its life as a main sequence star, where it peacefully fuses hydrogen into helium. We saw all of that. But yeah, here's the thing. Nothing in the universe lasts forever. Even stars, which can live for, billions and billions of years, eventually have to grow old. So now we shall see the journey of a low mass star, which is, less than eight solar masses. And yeah, here's something that makes this, journey really exciting. Our own sun belongs to this category. So yeah, we'll be literally seeing the future of our sun. And trust me, guys, it is a very engaging process. And yeah, we will for sure be, mind blown by the universe. Okay, let's get started. So, okay, now first of all, this transition, isn't happening anytime soon. Our sun still has around 5 billion years of fuel left. So we have got plenty of time. We are now in this main sequence stage. So our sun will become a red giant, planetary nebula, and eventually become something called white dwarf. And that's the journey we are going to follow from now on. So yes, I want you guys to keep the into high. It will for sure be an interesting journey. So yes, let's get started. So before we see, how that happens, let's first answer one basic question. Where exactly are we today in the sun's lifetime? So yeah, if you could see, we are here in the HR diagram. So we'll be seeing mainly four phases: RGB and helium flash occurs and it transitions to HP and yeah to AGP at last. Yeah, I mean, if we compare the sun's entire lifetime to a human life, our sun is kind of what to say, a middle-aged adult. So it's about 4.6 billion years old, and yeah, scientists estimate that it may live for about 10 billion more years. So it's almost halfway through. Right now, our sun is a main sequence star. That means it's right now converting its hydrogen into helium in its core. And yeah, that's exactly what gives us light and heat every single day. And one more question is that where will we be in the future? Well, the sun won't stay like this forever. One day, the hydrogen fuel at its core will start running out. And once that happens, everything inside the star, begins to change. And yeah, our sun slowly transforms into a red giant. That is what our near future will be. Let's see that. Yes. Hmm. Okay, all right. Now our sun starts, getting old. For billions of years, the sun has been converting hydrogen into helium inside its core. But eventually, the core hydrogen, right, it becomes exhausted. Notice I said core, there's still hydrogen in the outer layers, but the center of the star has run out of fuel. So let me ask you something. If the outward pressure produced by fusion becomes weaker, what do you think gravity will do? Exactly. Gravity wins. So the helium core, starts contracting. And whenever something gets compressed, it eats up, right? So the helium core becomes smaller, but also hot at the same time. But here's the surprising part. Even though the core is shrinking, the outer layers of the star, expand enormously. This happens because hydrogen surrounding the core is still undergoing fusion. It produces, enough energy to push these outer layers outward. As the star expands, its surface temperature also decreases, and cooler stars, appear more reddish in color. And yeah, here's a beautiful example. Okay, the star is Arcturus. It's one of the brightest stars we can see in the night sky, and it's actually a red giant. So when we look at Arcturus today, we are not just looking at another star. We're actually looking at the stage that our own sun will reach in about 5 billion years. So yeah, this stage is what we call red giant branch. To summarize, core hydrogen gets exhausted, the helium core contracts and eats up, the outer layers expand, and the sun becomes a red giant. Yeah, but the core keeps getting hotter. And once it reaches about 100 million Kelvin, something extraordinary happens. It's called the helium flash. Mm, okay, our sun is now a red giant. And if you look at this image, the star appears huge and bright from the outside. But the most important event is happening deep inside the core. Uh, okay, where we cannot directly see it, but yeah, this is what we call helium flash. Remember what happened in the previous slide? The helium core kept contracting and heating up because gravity was squeezing it. Eventually, the temperature reaches about 100 million Kelvin, and at that temperature, helium nuclei, right? It finally gains enough energy to start fusing together. This fusion suddenly ignites in the core. Now, the word flash make it sound like the star explodes, but yeah, that's a very common misunderstanding. The star does not explode and all. The flash happens, deep inside the core, and most of the energy, right, it is observed internally. So yeah, from the outside, astronomers do not see a giant explosion. And also note that during the stage, helium nuclei fuse to form carbon and oxygen. And yeah, this is a really important moment because many of the carbon and oxygen atoms later they become part of planets, I mean oceans And yeah, look at us even. We are carbon based, right? So even though the star, looks calm from the outside, its core has, just switched on a completely new type of fusion. I mean, it's comparable to us, right? Like outside, we may, we would like to look nonchalant, but yeah, inside we do have that nerve to express ourselves. Okay, coming back. Until now, the star was, mainly powered by hydrogen fusion. Now helium fusion has begun. And once this new fusion process stabilizes, the star enters a more balanced stage called the HB phase, which is horizontal branch phase. Okay. Yeah, in the previous slide, we saw helium flash. Now you might think, what happens after such a dramatic event? Well, the star finally becomes stable again. If you notice this picture carefully, the star is, no longer as big as it was during the red giant stage. I hope you guys could see the size. That's because the star has now settled into a new balanced state. Earlier, only hydrogen was undergoing fusion, but now helium fusion has also started in the core. So, yeah, now the star has two fusion regions, fusion in the core and fusion in the shell around the core. Yeah, that's why this stage is much more stable. I mean, there are two forces compensating gravity, right? So compared to the red giant stage, the star actually shrinks a little. It also becomes hotter at the surface. But yeah, this stage also doesn't last forever. Eventually, the helium in the core, right? It also gets used up. So yeah, when that happens, our star enters the next phase of its life, which is AGB, asymptotic giant branch. Okay, okay. Our sun has now finished another stage of its life. During the previous stage, helium was fusing in the core, but just like hydrogen, helium is also a fuel. And yeah, eventually it also gets exhausted. So what remains at the core is a carbon oxygen core. Now here's something interesting. This carbon oxygen core is not hot enough to fuse carbon. So the core becomes inactive. But yeah, the star doesn't die yet. Instead, the fusions, right? The fusion reactions shifts to the layers surrounding the core. Here, helium is still undergoing fusion, and yeah, just above that, hydrogen is also undergoing fusion. So now, unlike the previous stage, the star has two active fusion shells: an inner shell where helium is fusing, and an outer shell where hydrogen is fusing. Yeah, that's exactly what this picture is showing us. Yeah, and now our core is carbon oxygen core. Since both these shells are producing energy, the outer layers expand once again. Yeah, and it makes the star become a giant for the second time. Yeah, that's why this stage is called the asymptotic giant branch. I mean, it's a asymptotic behavior, right? It was normal and become a giant, became normal again, and yeah, became a giant for the second time. So yeah, but this stage is also very unstable, and soon the star starts, losing its outer layers into space. This leads to the formation of something called protoplanetary nebula, which is a short transitional stage before a true planetary nebula forms. Let's see that. Okay. Mm, okay, we saw that the star had reached the AGB stage. Yeah, and at that stage, the star became very unstable and started losing its outer layers. Now, before starting, let's take a look at this beautiful image. Okay, this is called the Egg Nebula, which was, imaged by Hubble telescope, and yeah, it's one of the best known examples of a protoplanetary nebula. It get its name because simply it looks like an egg, nothing special. Okay, I mean coming back. So in AGB phase, the star starts ejecting its outer layer, and everything you see surrounding it. all these clouds was once part of the very same star. A dense shell of gas and dust starts forming. The star is now blowing away its outer layers through something called powerful stellar winds. So yeah, this is a star, literally returning its material back to space. Now, don't get confused by the name proto. Proto simply means yearly or first stage. So yeah, protoplanetary nebula is simply the stage before a true planetary nebula forms. At this stage, the central star is becoming hotter and hotter, but it is not yet hot enough to make this surrounding gases glow brightly. And yeah, once the exposed core reaches above 30,000 Kelvin, I mean, when it is ready to ionize the surrounding gas, its intense UV light, starts lighting up all the surrounding gas. So yeah, that's when we get to see one of the most interesting objects in the universe, which is Planetary Nebula. All right, just take a moment to look at this picture. This is called the Cat's Eye Nebula. Yeah, I mean, it's comparable to our eye, right? So, yeah, you might even wonder, I mean, is this real? Yes, this is an actual image captured by astronomers. Now, remember the previous slide, the star had already thrown away its outer layers. Now, the central core has become extremely hot, so hot, in fact, that it starts emitting this UV radiation. That UV light strikes the surrounding gas, and this excites the atoms. Simply saying, when atom gets excited, it emits light, right? So yeah, that's why the gas begins to glow, creating this beautiful colors. So what you are seeing here isn't some huge explosion or something. It's just glowing gas that once belonged to the same star itself. Now, the name Planetary Nebula might be, a little misleading. I mean, it has nothing to do with planets. When early astronomers looked through, telescopes, these glowing clouds look like planets. Yeah, so that's why they call them Planetary Nebula. So if someone asks you, are planets being formed here? The answer is no. Okay, the star itself is still there, but it has almost, lost all of its outer layers. And very soon, only the hot central core will remain. And the tiny, highly dense object is what we call the white dwarf. Okay, after the planetary nebula, drifts away into space, only one thing is left behind, which is white dwarf. And yeah, this is what our sun's final stage will be. Now, look at this comparison. Even though a white dwarf contains almost the same mass as our sun, it's only about the size of the Earth. I mean, just you can imagine that for a second. They say about 1.3 million Earths can fit inside the sun. So it's like almost our entire sun compressed into something about the size of Earth. Yeah, that makes a white dwarf one of the densest objects in the universe. Now, here's an important point. Yeah, white dwarf is not producing energy through fusion anymore. I mean, the nuclear reactions have stopped. So yeah, you might wonder. I mean, if there's no fusion, why doesn't it, keep collapsing under its own gravity? The answer is something called electron degeneracy pressure. I mean, Tirsilvi has perfectly explained it a few minutes ago. I know the name sounds complicated, but the idea is actually, simple. Imagine you are inside a crowded lift. I mean, more and more people keep trying to enter, but after a point, there's simply no room left. So yeah, no matter how hard you push, you can't squeeze everyone into the same space. Inside a white dwarf, something similar happens, but with electrons. They resist being squeezed any closer together, and yeah, this resistance is what we call electron degeneracy pressure. and it's strong enough to balance gravity. So yes, even without fusion, the white dwarf remain stable. So yeah, this tiny object is really the exposed core of the original star. And yeah, this is not the end. And eventually it becomes something. And yeah, it's a bit of suspense. I want you guys to think about it. But before we talk about that, I mean, what do you guys think? Is that really the end? Our sun has become a white dwarf. Its nuclear fusion has stopped. It slowly, cools over billions of years. So yeah, everything seems peaceful, right? It looks like the star has finally, found its retirement. What do you guys think? I mean, this whole journey is kind of interesting. I mean, you may think it's a never-ending cycle, but yeah, it does have an end. Okay, let's get started without, further delay. Also, before we see the end, is something that we gotta understand. Okay, our white dwarf is, probably thinking, okay, finally I can rest. But yeah, of course, our physics has other plans. An Indian physicist named Subramanian Chandrasekhar asked a very simple yet powerful question. He was like, okay, wait a minute. Can every white dwarf really remain stable forever? Or is there a limit to how much mass white dwarf can support? And yeah, and that one question completely changed our understanding of how stars evolve. He realized that a white dwarf can exist only under a very important condition. Let's see what he discovered. Yes, it is the Chandrasekhar limit. This is Subramanian Chandrasekhar, an Indian astrophysicist. He wondered whether every white dwarf could remain stable forever. After carrying out, detailed calculations, he made a remarkable discovery. He found that white dwarf can support itself only up to a certain maximum mass. And yeah, this maximum mass is called the Chandrasekhar limit. The value is approximately 1.44 solar masses. So a white dwarf remains stable only if its mass is less than about 1.44 times the mass of a sun. You can think of it as a tug of war. On one side, we have air-ground inertia pressure, trying to hold it up. On the other side, we have gravity, trying to crush the white dwarf. As long as the white dwarf is, below 1.44 solar masses, these two forces remain balanced. So yeah, the white dwarf stays stable. I mean, you guys will wonder what happens if it's above 1.44 solar masses. Well, it becomes something called Type 1a supernova, and yeah, huge explosion will occur, and only supernova remnants will be left behind. But the thing is, it only happens in a binary star system, that is a two-star system. Now, in the story we have been following today, the life of a sun-like star, this situation doesn't normally happen because our sun's white dwarf will be, much lighter than this limit. And yeah, it's only a single star system, right? So yeah, for stars like our sun, the white dwarf remains stable and simply cools over a long time. Okay, for this amazing work in astrophysics, he was awarded the 1983 Nobel Prize in Physics. So if you remember just one thing from this slide, a white dwarf is stable only below, about 1.44 solar masses. Before we move forward, let's look at the derivation. I mean, I have made it as simple as possible. I just want to show you the basic idea behind how Chandrasekhar arrived at the famous number 1.44 solar masses. Let's start with this first expression. This represents the gravitational energy of the white dwarf. What is gravity trying to do here? It wants to, pull all the matter inward and compress the star. So you can think of this equation as representing gravity, trying to crush the white dwarf. Now let's look at the second expression. This represents the relativistic energy of the electrons. Remember the previous slide, we learned that electrons create electron degeneracy pressure, which resists gravity. Here, n is number of electrons, and yeah, h bar is reduced Planck's constant, which is h by 2 pi. So while gravity is pulling inward, the electrons are pushing back. So yeah, now we have two competing effects. I mean, what do we do? We simply ask one question: when is the star perfectly balanced? That happens when the inward pull due to gravity is exactly equal to the outward pressure from the electrons. So yeah, we mathematically equate these two expressions, and after simplifying and substituting, as you can see, we arrive at this beautiful result, which is 1.44 solar masses. Okay, we learned about Chandrasekhar limit. Okay, now what? So yeah, our white dwarf has survived. It has finished all its nuclear fusion. We thought that the white dwarf can finally rest, but yeah, yet the universe says just wait a few trillion years. The thing is, yes, it's not over it. It simply keeps losing its leftover heat, and yeah, it starts cooling down. And slowly, for an over an incredibly long time, it becomes so cool that it no longer emits any visible light. And guess what? It becomes something even more mysterious, which is, yes, black dwarf. I hope some of you guys, predicted this. I mean, it is not a black hole. We have, finally reached the last stage in the life of a sun-like star. Yeah, this is called black dwarf. Remember, a white dwarf doesn't produce any new energy. It simply shines because it is still hot, but over a very long time, it keeps losing that leftover heat. So yeah, slowly, it becomes so cold that it no longer emits any visible light. Yeah, that cold, dark remnant, which is what we call the black dwarf. Now, here's something really interesting. Yes, it's just a hypothetical stage. No black dwarfs exist in the universe today. Why? Why? Because the universe is about 13.8 billion years old, and yeah, simply it's not enough time for a black dwarf. I mean, sorry, my bad. White dwarf to cool all the way into a black dwarf. So black dwarfs are something that scientists predict will exist in the very distant future. So yeah, with this, we have completed the entire life cycle of the stars, just like our sun. Yes, we transition from main sequence star to red giant to planetary nebula, white dwarf, and finally to here, black dwarf. We have actually seen the future of our own sun, but here's something. Our sun is only an average size star. And what happens if a star is, much more massive? Let's say more than about 8 times the mass of the sun. Do they also become white dwarfs? I mean, the answer is definitely not. Their ending is far more violent and more interesting as well. So yes, now let's get through the life cycle of massive stars. And for that, I give my lead to my friend Thiruselvi. Yes.
Yeah. Thank you, Gautama. Okay. So till now we have been seeing, how the fate of low masters looks like, right? But well, when a star starts its life with more than 8 solar masses, it usually lives fast and dies out. Meaning that these cosmic heavyweights they are destined for a far more violent finale. So yeah, let's get started to see how their evolution is going to look like. So after fusing all their hydrogen into helium during their main sequence stage, they rapidly swell up to become what is called as red supergiants. So they are the largest stars by volume in the universe. Now, before I continue this, Like take a look at this background image which I have here. So this was captured by ALMA. So this shows the sharpest image of a star which was ever captured. Now what I want you to do here is to guess what this star, which star this might be. I will give you a clue that this star is red supergiant, one of the most famous ones, which is located in the constellation of Orion. It can take some 5 seconds to guess right what the star might be. Okay. So if your answer was Betelgeuse, then you can give yourself some claps because yes, that's the right answer. So this star this is actually the image of Betelgeuse. Now Betelgeuse, it's actually a celebrity star, because astrophysicists they watch it second by second. Now, what makes it that famous is because it is basically a ticking time bomb, like which is already at its edge of undergoing a violent supernova finale, where it is expected to explode out and blast out and all. Now, the thing what makes it very interesting is if ever undergoes blast in the near future, it will be so bright that it will be even visible in the broad daylight. We can see the blast leftovers along with when we are seeing the sun also. So that's why it is famous. I hope we see this at least before we die. I hope we have that luck, but it is expected that we can see that in near decades. Okay, now let me introduce another star here, which is the Antares. So this is located in the Scorpion constellation when you see from the Earth. Now let me compare their sizes here. So if you compare, you can see how voluminous they are. The Antares and Betelgeuse, they are really a giant compared to the dot-like structure, which is representing our sun and other stars like Sirius. It is one of the brightest stars, right, in our night sky. And Rigel, it is one of the massive blue giants in main sequence fields. So these stars are very small compared to them. And that's why these red supergiants they earn this nickname that is cosmic behemoth because they are very voluminous. Now, yeah, let me walk you through some basic characteristics which you might find in a typical supergiant. The first is they are incredibly, extremely unstable. That is, they also exhibit some frequent violent pulsations. Why so is because there is a breakdown in the star's internal balance. That is basically the hydrostatic equilibrium is maintained by a very delicate balance. It is a bit broken now. Why so is the massive star like this, they often fuse their elements as a series of concentric shells. So once a new shell ignites, that ignition is actually not very smooth. It is very sudden. So the sudden ignition sends some sudden thermal shock waves, which will cause their outer atmosphere to expand and contract violently. And that's why we have these pulsations. And because of that breakdown, we say it is extremely unstable. Now, coming to the second thing, these giants they produce incredibly strong stellar winds. Why so is because of their core's luminosity. This luminosity is actually staggeringly very high that they actually create immense radiation pressure. So when this pressure actually slams onto those loose outer layers, it strips away those outer layer away from the star in what is called in the form what is called as stellar winds. And this winds can be so powerful that the star might end up losing some solar masses, even one solar mass of its mass in just 1,000 years or even just 1 year it can keep shedding away its mass. It is a typical one, it has already been observed in the real-time observations, and that's why I thought of it mentioning here. And next, coming to the third point, unlike our sun, which will die after fusing all its helium, massive stars they can provide crushing gravitational pressures, which can actually heat their core to billions of degrees of temperature. So this actually allows them to drive this multi-layer core fusion, where they will be bonding progressively heavier and heavier elements in success in some series of successive shells around the core. And that process through which this happens is called stellar nucleosynthesis. But this nuclear engine, which is keeping the star alive, will die out after some time. And once it stops, what we have is this type 2 supernova. And that actually marks the end of the star's life. And after that is what we will be having the neutron star or black hole. Now, this last two are very important, so I'll try to explain them in detail. Yes. So now we have the stellar nucleosynthesis. So if you want me to define them, so it's basically a cosmic process by which the elements they are fused inside the star's core. I mean, with all those nuclear fusion reactions. Now, as you can see in this diagram, the star actually develops a distinct onion-like structures of concentric shells. Like in each shell, you have different element which will act as a fuel. Now, if you can look at this timeline table, as you can see, there are several burning stages. And if you consider the hydrogen to helium burning, that actually takes 7 million years. It's a high period. But if you see, it is progressively decreasing rate. And at the end, we have silicon burning, which will burn out all its silicon in just one day. So basically, the clock is taking at a very alarming rate. Now let me focus on the burning stages. So first, once you have helium core, what will happen is the helium burning stage, and then we go to carbon burning, neon burning, oxygen burning, and silicon burning. Now let me briefly explain about what these burning stages are. So first is the helium burning. So once this helium core is formed, right, once its the core temperature hits this 100 million Kelvin mark, it will this burning stage will start. As you can see from this diagram, what happens is three helium nuclei they fuse in the rapid succession to create a stable carbon 12 atom. So this process is called triple alpha process. So if by chance this carbon 12, if it captures another helium nuclei, then it creates the oxygen 16 atom. So by the end of this burning stage, what you have is a carbon core with some amount of oxygen, and with the remaining leftover helium, right, they will form a shell around this core. Now, once this carbon core's temperature hits somewhere between this 500 million to 1 billion Kelvin, we have this carbon burning stage. It will officially initiate. Now, this here we have this carbon carbon process where when this two carbon atoms fuse with each other, they produce an excited state of ignition, which is really unstable. Now, in order to attain stability, it can decay through three branches, which I have shown here. But the most dominant one is the branch one, which is called as neon plus alpha channel. Now, this produces neon and alpha as the products. So by the end of this burning stage, what you'll be having is the neon core with some amounts of sodium 23 and magnesium 23 surrounded by the leftover carbon as a shell. Now, once this neon core hits the temperature of about 1.2 to 1.5 billion Kelvin, we have this neon burning stage. Now here what happens is this neon, they start undergoing photodisintegration where they produce oxygen 16 and alpha particles. Now these alpha particles, they get captured by the remaining neons and they produce magnesium 24 and some gamma ray photons. Now by the end of this burning stage, you will be having a core which is most dominated by oxygen and some amounts of magnesium surrounded by the leftover neon as a shell. Once this oxygen core hits this 1.5 to 2 billion Kelvin temperature mark, then we have this oxygen burning stage. So here, two oxygen nuclei they smash together to give a very unstable nucleus called sulfur 32. Now this, since it's unstable, right, so it can decay through these three channels which I have shown here, which is very similar to the carbon-carbon process. Now here the most dominant one is the silicon channel, which will produce silicon and alpha particles. So at the end of this whole burning stage, what you will be having is a core dominated by silicon and some amounts of phosphorus 31 and sulfur 31, and it will be surrounded by the leftover oxygen atoms as a shell. Now moving on, what we have is the silicon burning stage. Now once the silicon core hits the 3 billion Kelvin mark, then this whole burning stage will start, and it will just take a 1 day to fuse all the silicon into iron, and that's why we call it 24-hour furnace. Now, if looking at the core mechanism, yes, it again undergoes photodisintegration, which will give magnesium 24 and streams of alpha particles. Now, these alpha particles, they get captured by the remaining silicon 28 nuclei, which will kickstart, unlike the neon burning, it will here kickstart a consecutive chain of alpha additions called as alpha ladder process. So as you can see right here, the series of these reactions are what is called the alpha ladder. Basically, once when the helium it gets added and added, the element its atomic number will go higher and higher. So that yeah, it forms a ladder. That's why we call alpha ladder. Now, if you look at the ultimate end product, then it is nickel. Nickel 56 marks the end of the alpha ladder. Now, this the thing with nickel 56 is it's actually highly radioactive and it's unstable. So, as a result, it undergoes successive two stages of decay to give out stable iron 56. Now, by the end of this 1 day period, now all the silicon would have been converted into iron, and what we have now is the iron core. Now, right here, the entire engine it basically stalls. Then all the nuclear fusion reaction will stop here in the core. Now, that means the iron forms the dead end of the star. So, why is the iron the cosmic dead end, or like what is the physics behind them? Like, why the nuclear reaction stops? Okay, let's try answering all these questions one by one. So, it all comes down to this concept which we already know called nuclear binding energy per nucleon. This graph you have already studied in your 12th, right? In the nuclear physics chapter. So this energy per nucleon, it actually tells you how much stable atomic nuclei is. If this energy is high, then yeah, atomic nuclei is also very stable. So taking that logic here, it means that iron actually forms the peak here, which is represented by that yellow dot. So since iron is the peak here, it basically means that iron 56 is the most stable, thermodynamically the most stable nucleus in the entire universe. And this is also the reason why certain elements they undergo fission and certain elements undergo fusion. If you take lighter elements like helium or carbon, oxygen, they often fuse with each other to give out heavier atoms, which will have more binding energy per nucleon than them. So by that they basically attain stability. So in that fusion reactions they release energy, and that is what will create that outward pressure, and it will basically keep the star alive. But once we reach this iron or any elements which are heavier than iron, they prefer fission. That is, they try to break down into lighter atoms. Whose binding energy is greater than them per nucleon is greater than them. So as a result, when this iron core forms, what basically happens is when we force them to fuse, they will start absorbing heat instead of releasing them. So as a result, there is no exertomic energy which is being released. That means no outward pressure will be there once the iron core forms. So without that, there will be no nothing to fight the gravity. Right? So basically, there is an imbalance in the star's balance mechanism. So as a result, the gravity it will use up this chance. It's a evil here. So it will dominate and it will trigger an immediate catastrophic explosion, which we often call as core collapse supernova. Now, this supernova doesn't just happen, in single step. There are series of steps which will guide it bit by bit. So I will explain in detail how they are. So it's a very easy one if you understand it very clearly. Okay, let me start like what they are. So first, what happens is we have iron core, right? So it is surrounded by the leftover silicon atoms. Now the silicon is still bonding, like fusing all like within each to give the iron atoms. So basically, the iron core is growing. So once it grows out and exits this Chandrasekhar limit of 1.44 solar masses, instantly the electron degeneracy pressure rates, which can sustain against the gravity, it will start being crushed down by the gravity here. So as a result, the gravity will dominate and it will start the cause the outer layers to fall onto the core at the massive fractions of speed of light. And that is what we call as catastrophic core unfold. Now, when this is happening, the matter is basically getting crushed, right, because of the gravity. Now, because of that, the density will increase. But once it hits this critical density called the nuclear saturation density, which is the density found inside a typical atomic nucleus. So once it reaches that threshold density, the quantum rules they bring out a new pressure, which is called as neutron degeneracy pressure. Now, this is very similar to the EDP, which I discussed earlier. Like all the laws are same, all the behavior is also same, but the only thing is they are caused by neutrons, nothing else. Now, once this kicks in, like as I said in EDP, what happens is it will cause the core to get locked in place, meaning now it can neither contract nor expand. So this will basically mean that the core now will act like a brick wall, like solid brick wall. So the infalling layers, which are like falling onto it, will smash and get violently rebounded back. And that process is what we call as core burn. So this core burns will result in a massive outward shock wave. Now this shock wave, it isn't very smooth, when it goes out. It actually faces different barriers in its path, which are nothing but two massive energy drains, which will eventually drain out its complete energy, which drives this whole shockwave, and it will stop this shockwave to get stalled at some point, at some higher radius. And that shockwave is what we call a stalled shockwave. And if you ask me what are those energy drains are, that they are this photo disintegration and ram pressure. Basically, what happens is when this shockwave is going out, it most of its energy gets spent in breaking down the heavy iron nuclei which it encounters on its path, and it breaks down them into protons and neutrons. And another fraction of its energy will be spent when it slams onto the infalling layers. There are still some infalling layers, so when they both smash, some of its energy gets lost there. So as a result, it will get completely drained out of its energy and it will get stalled at some higher radius. Now, when this is happening here, there's something else which is being cooked in the core, which will ultimately revive this shockwave. So in core, what is happening is basically experiencing some extreme electron capture reaction. So it is a reaction where the protons and electrons they are forced to fuse with each other to give neutrons and neutrinos. So okay, let's not focus on neutron here, but here this reaction actually produces unimaginable torrent of neutrinos. Now the thing about neutrinos is they are called ghost particles, meaning that they weakly interact with normal matter. So that makes them the only beings which are capable of escaping this very highly dense core, like unlike the shock wave. Now another thing is they possess about like 99 percentage of the total gravitational binding energy of the this collapsing star. That's a huge energy, right? But so that means as a result of this process, they start moving out of the core now. But the density is so high here that just it makes sure that just 1% of these neutrinos get trapped in those the stall shock wave. So this when this 1% is trapped, its energy will get absorbed by this shock wave, and this tiny 1% will inject a massive wave of heat and pressure in the shock wave, and that is what we call as unstalling. It basically revives the shock wave violently. So this violent revival, it causes the shock wave to drive through the star, and it will result in this runaway explosion, as I have shown here, which is called a core collapse supernova. So I hope you understood how this, the process gets built up bit by bit. Now take a minute and understand that this split second explosion, it actually creates extreme conditions which cannot be replicated anywhere else in this universe. So this extreme reactions is what will drive another very significant process called explosive nucleosynthesis. Why it is important, you'll understand at the end of this, like when I explain this process. So yeah, let me explain what are the stages you have here. So basically, simultaneously while the core collapse is happening, then when the shockwave gets revived, right? So it actually causes the temperatures to go well beyond the threshold temperatures which are required for silicon and oxygen burning. And that's why they result in instant synthesis of iron peak elements. Like for typical silicon burning, we it takes 1 day, right? Oxygen burning it takes 6 months. But because of this extreme condition, they happen in just some fraction of seconds. So in fraction of seconds, it creates iron peak elements like cobalt, nickel, manganese, chromium. So they are the iron peak elements. But the far more important process is this R process, which is also known as rapid neutron capture. Now, the same revived shockwave, when it goes, drives through the outer layers, it basically creates certain zones where the density of the neutrons will be very high, and their flux also will be very, very high. So, as a result, what happens is there will be some iron and nickel nuclei which will be there in the zone, So basically, these neutrons they will bombard onto those nuclei at very extreme speeds and with very high flux. So when you take a normal stellar atmosphere, what happens is when a atom, when a nuclei, when it captures a neutron, it will have some time to undergo radioactive decay to produce a stable atom. But here, this neutron influx is so high that the this iron and nickel nuclei they will capture a new neutron before they even have some time left to undergo decay. So as a result, they keep building up this huge number of neutrons, and thus it will make this whole nuclei unstable. But after some times, once this shockwave passes away, like it passes after some time, the influx will go down. So as a result, the unstable nuclear, it will use up this time to undergo the beta decays, which will convert all their neutrons into protons. And that is how they basically jump up this periodic table. And this is how it ends up forging some of the heaviest and most precious elements in the universe, like gold, platinum, yeah, silver, uranium, thorium. So these all were synthesized in this process. Now I have explained this. Now take a minute and understand that without this chaotic split second finale, this whole universe night would be completely devoid of all the heaviest and precious elements which we know, which are used for making our advanced technologies, which are required for building rocky planets or even sun, etc. And that's why this explosive nucleosynthesis is very important. So I hope you understood. Now, okay, this explosion has occurred. Now, basically, what happens is occurs is in a blinding flash of blast, and what remains after this explosion is a dead remnant, which we often call as neutron star. Now, there is actually a limit here, like just like Chandrasekhar limit, which will decide this remnant is either neutron or proton, like sorry, neutron star or black hole. So that limit is called as TOA limit. I'll be explaining that in a while. But here, let's assume that the mass of the core is well beyond the TOA limit. So what we have as a result is this neutron star. Okay, so now let's take a quick look at how their birth looks like. So that happens simultaneously during this whole core collapse process. Now, during the core collapse, what happens is the matter they will pass through three critical density thresholds. The first is when they cross this 10 power 9 threshold, it ignites the process which is called electron capture. I explained it right. So this process is what will generate those neutrons and neutrinos. Now, neutrinos they install the stalled shockwave, and neutrons they end up becoming the part of neutron stars. Now, once it hits the next threshold, which is the 4 into 10 power 11, they start exhibiting a phenomenon called neutron drift. What happens here is the nuclei, they get so much oversaturated with neutrons, basically. So, as neutrons, they keep on building in nuclei here, it basically brings down their binding energy per nucleon, which will make it eventually unstable, like I have mentioned earlier, right? So instead of taking some time and converting them into proton, they some of these additional neutrons they also leak out of the nuclei and they leak out into the empty space, and that phenomena is what we call as neutron drift. Now, the thing here is, right now you can distinguish what an atom is, what the free space filled with the neutron is. So there is a boundary which separates them. But once we reach the third threshold, which is also called nuclear saturation density, the 2.8 into 10 power 14. Now, here that boundary which distinguishes the atom and the free space will actually dissolve. That is, it will vanish off. Basically, here the nuclei will dissolve completely. And right now, the star's core, they transition from a huge lump of separate atoms into a uniform fluid of degenerate neutrons. So, right now, what we have as a result is a neutron star, which is basically nothing but a fluid of neutron particles. Now, if you take a close look, the same neutron saturation density is also where the quantum rules they bring out that pressure, which we call as NDP. Now, NDP will I will explain the role of the NDP like in a while. So before we enter into the physics and math domain, let's first refresh ourselves with some facts about neutron stars. So now, let's take a look at this spectacular image on the screen which we have here. So this is a real X-ray capture from NASA's Chandra X-ray Observatory, which is showing a pulsar called Vela pulsar. So it is nothing but a rapidly spinning neutron star which is blasting out jets of electromagnetic radiation. So this is how the typical behavior of a neutron star will be like. Now, the tiny dot which you can see, right, like it is arrow marked as pulsar. So that tiny dot at the center is actually is equivalent to the entire sun's worth of mass being crushed into sphere which is no bigger than 12 miles across. That's such a I think you can understand the scale here, right? So that basically skyrockets this density of the neutron stars to very high value. So if you want to understand the scale, you can try taking a single teaspoon of neutron star material. So that would weight about 1 billion tons on Earth. So basically, one teaspoon of neutron star is equivalent to the weight of Mount Everest. So that is how extreme and exotic these objects are. Now, one more thing which I would like to emphasize here is the terms like pulsar or magnetar or quasar. They are the common category names which we use instead of using this term neutron star. So these terms you will typically see in all the scientific papers or the news or anything. Okay. Now, yeah, if you take a look at their nicknames, yeah, first this it is they are stellar corpses. Okay, you know why that is. And next they are also called as cosmic lighthouses. Why so? Is yeah, let me first point out to one of the image here. Yeah, in this neutron star slide, I guess you can see this fourth image, right? Bottom right. So this is how a neutron star will spin. Basically, the neutron star here it shoots out the jets of radiation, right, out of their magnetic pole. But simultaneously, the star is also rotating. So as a result, these beams will sweep across the universe, just which whose behavior is similar to a typical lighthouse which we see on Earth, and that's why we call them the cosmic lighthouse. And this is how they spin, as you can see in the fourth image. Now, if you look at the first image, that is how they actually appear when we see from our Earth. So, from our perspective, their light it usually appears to blink, like pulse on and off, and that is also the reason why these neutron stars are sometimes called as pulses. This defines the characteristic of them. Okay. So now, yeah, let's take a look at the defining characteristics of this star. But remember that they were actually born out of very extreme conditions, right? That actually makes this star place with very, much more mind-boggling extremities. So yeah, let me walk you through what are the extremes which you can find here. So first is they have extreme gravity. That is, their gravity is about like 200 billion times stronger than that of Earth. So if you want to compare the scale here, then if you drop a object, like imagine you are dropping an object from about like 1 meter from its outer surface, then it would actually slam onto that surface at over 7 million kilometer per hour in a single microsecond. So I hope you can understand how extreme that is, right? So here the gravity is very powerful. So yeah, they actually bend that space-time fabric beyond the classical limits, just like those black holes. Now, yeah, coming to the next extreme, what we have is their extreme rotation. Yeah, we know they are the fast spinners, right? If you ask me how much they spin, they rotate up to about like 700 times per second. That's a huge rotational speed, basically. And why so is because of a concept which we know that is the conservation of angular momentum. Now, yeah, I won't explain. You can basically, after this session, you can try to see how we are applying the angular momentum here. Yeah, that's your work after the session. Now, yeah, let's go to the next extreme, which is they exhibit extreme superfluidity and superconductivity. Now, on Earth, now, we try to reduce down the temperature near absolute zeros for the matter, like everyday matter, to actually exhibit these properties. But neutron star, they does it like at some extreme temperatures, like high temperatures, like hundreds of millions of degrees. So these so this actually makes them the highest temperature superfluids or superconductors, which we know in the current known universe. But if you wonder, what superfluid is, then superfluids are the fluids with zero viscosity. There is no friction between the layers there. And superconductors, that they conduct electricity with zero resistance. That's it. Now let's move on to the next extreme, that is their extreme magnetic field. So their magnetic field is like trillions of times stronger than that of Earth. And we also have a separate class of neutron stars which are called magnetars. Their magnetic fields, they are 1,000 times stronger than a typical neutron star, and that's why they earn a special name. Okay, now looking at all these extremes now, see, it is naturally it's natural to ask that how what on earth is actually sustaining this neutron star, from undergoing the gravitational collapse. So that is nothing but first this neutron degeneracy pressure. Yeah, it is similar to EDP because all the quantum rules are same, all the characteristics are same. So I'm not going to explain anything here. But so keeping that in mind, let's move on to this particular paradox, 1939 paradox. So this is, in 1939, what the physicists did is they assumed that the neutron star was filled with free neutrons which do not interact with each other. By assuming that, they try to calculate the TOV limit I mentioned earlier. Right? So they tried to calculate this TOV limit with all these assumptions, and they ended up with the value of zero point 0.7 solar masses. But if you actually see the some of the actual neutron stars which you can observe in the universe now, they weight over about like some 2 to 2.1 solar masses. So that basically means that NDP here is actually insufficient to hold that much excess weight. So that means something must be backing up against the gravity, right? So yeah, that is nothing but the strongest force in the entire universe, which we know that is namely strong nuclear force. Yeah, let me explain what the role of strong nuclear forces is. So I guess you can see this right, modified EOS. What is EOS? Yeah, we actually saw this in EDP itself. So it is nothing but a mathematical equation which will bring out some relation between pressure and density or sometimes temperature. We saw in EDP, right? The pressure is equal to constant into density power 5 by 3. So that is nothing but EOS. Now we call it modified EOS here because okay, for that, let me provide the example analogy of ideal gases and real gases. Ideal gas. Now, for them, we assume one of the assumption is there is no interaction between the gas particles. And with stating that assumption, we actually calculate and we derive what is called ideal gas laws. But we actually deal with real gases, right? So when we are dealing with them, where these interactions are possible, we basically what we do is we apply some modification onto the ideal gas equations, and we try to apply them on the real gas, and that's how we solve any problems we have. Now that is the same case here. So the typical ideal equation will be P total will be equal to P due to NDP, that is the degeneracy equation. But here, since we have this interaction forces, which are called strong nuclear forces, we add a modification term here, which we call like P nuclear. So this is actually derived from the potential energy of those nucleons. So nothing else. Now this modification term, it can be both positive or negative, depending on whether these forces are attractive or repulsive. So if we are dealing with the distances which go from 1 to 2 femtometer, this is usually what we see in everyday matter. So there, the speed nuclear is always, and what we have as a result is the soft EOS. So meaning is that the matter here it is like extremely squeezy and we can compress it very easily. But once when we come to this atmospheres which we have in neutron stars, there the distance between the nucleons they go well less than zero point 0.5 femtometer. So at that point, the strong forces they become the highly repulsive, and as a result, the speed nuclear will become positive. So this will basically skyrocket that positive value and then the total pressure here. So this is what we say will stiffen the EOS, and that's what we call it stiff EOS. Now the stiffening of this equation will provide that extra structural support, which will be needed to sustain that two solar mass cosmic giant from collapsing into a black hole. So I hope you can understand, right, how this strong solar nuclear forces, along with the NDP, they together work. How they together work and sustain the neutron star from undergoing a gravitational collapse. So I hope you understood this one. Now, this is not always necessary that they will keep on be sustaining it forever. There is a certain limit after which the gravity can dominate and it can crush the neutron star into a black hole. and that hard limit is what we call as TOV limit. So TOV limit, the full form is Tolman-Oppenheimer-Volkoff limit. So it is basically a cosmic breaking point. So if the neutron star is above this limit, then it undergoes the gravitational collapse into a black hole. Now, if you observe here carefully, the limit is actually not fixed here. That is, it usually goes between the range of 2.2 solar masses to 2.9 solar masses. Why it is not fixed is because we do not have an exact EOS. Because the EOS here we are writing when we are dealing with ultra high densities, right? Now those kind of densities cannot be replicated on Earth here. So as a result, the physicists they do not know the exact EOS. So as a result, they came up with some several mathematical models which gave different forms of EOS. So according to the equation which we choose, the value it usually fluctuates between 2.2 to 2.9. And that is also another thing which is the reason that is while calculating TOV, there was an assumption that neutron stars were considered non-rotating. But spinning is actually its key feature, right? But physicists they assume that it is non-rotating and they calculated it. So if you like account for its rotational component also, then it will actually boost this its TOV limit by some 15 to 20%. And that is also another reason why we do not have a fixed TO. Okay. Now let's take a look at what physics concepts which we use in order to find this limit. So here we throw away all the Newtonian laws of gravity and we try to incorporate Einstein's view here. According to his view, he said that space and time were fused into a flexible four-dimensional fabric, which we call a space-time fabric. So why we are dealing with general relativity here is that nuclear densities, those are very extreme conditions. So at those conditions, the Newtonian physics usually fails, and the general relativity they become mandatory because of the three main reasons which I have listed down. So yeah, let me talk about the reasons here. So first is the pressure sources gravity. Now this is what I will call the ultimate cosmic trap. Why so is in the classical physics only mass creates the gravity, right? But when we talk about GR here, energy and pressure can be expressed as a form of mass. Meaning now the pressure it will be contributing to the inward gravitational pull. Actually, it has to be opposing the gravitational pull, right? But instead, it will behave like a mass, and it will actually instead strengthen the gravitational pull instead of fighting against it, and that ends up causing one becoming one of the causes of the gravitational collapse. And so, basically, you have to understand that the star is literally digging its own grave here. Okay, we can't help it anymore, by the way. Okay, so let's move on to the second point, which is the severe space-time warping. So, as you already know, if the mass density is very extreme, then this space-time fabric will be bent beyond the classical limit. So that basically changes how the matter, behaves around it, or moves, or how this is going to, stay balanced, or etc. Now, okay. Now, next we have is the Newtonian error. Now, if you ignore all these things and if you try to use Newtonian math in order to calculate this TOV limit, then you will end up estimating a star which is which almost is on the verge of becoming a black hole. You will estimate the star to be very stable enough, and it can remain stable forever. So here, basically, Newtonian math it underestimates the this crushing power of gravity because it doesn't account for the about two reasons, right? That's why we have this Newtonian error. So basically, when we are dealing with Newtonian gravity, we have to try to incorporate some factors which will try to account for these extra like things which are here because of general relativity. So that brings us to this equation called relativistic balance equation. So please do not think that it is very complex. Let me try to explain it very simple. It's not very too complex at all. Now, if you observe that white part here, that is basically the hydrostatic equilibrium which we dealt in main sequence states. Now that Gm rho by r square, that is nothing but Newtonian gravity. So along with it, we are multiplying certain factors which we call Einstein's correction. As I said, they will account for all the errors which we have around the Newtonian gravity. Now let me quickly explain what these factors are. So first, what we have is the gravity of pressure. The first term is called like that. So it basically takes into account that the pressure has weight. because it can be expressed as energy density, right? Now, again, energy can be written as mc square, can be written as mass here. So yeah, thus the pressure has weight. And next, the second term is what we call as enclosed work factor. So this basically accounts for the thermodynamic work which is being done inside the some sphere of radius r. So basically, that sphere will be having massive internal energy inside it. So again, this energy can be mapped out as a mass, and thus it ends up, becoming a secondary source of the gravitational pull, and it will strengthen them. Then let's move on to the third factor which we have here called spatial matrix thing. So here, as you can see, it is like 1 divided by 1 minus Rs by R. So if you ask me what this Rs is, then this it's nothing but the Schwarzschild radius. So this is the radius of event horizon of a black hole. That is the point of no return for a black hole. Now, when the gravity is trying to crush, now it is basically causing the star's radius to approach this particular Rs radius. So basically, it will cause that 1 minus Rs by R, the denominator of this fraction, to become 0. So as a result, it will shoot up the whole factor into infinity. So meaning now the small Newtonian gravity which we had here will be violently magnified beyond the limits which we have, the classical limits. So this is what will finally source the gravitational collapse process. Okay, now let me come back here. So basically, why we use here this equation is to calculate the TOV. So that is not the only equation. We also use another equation which you have here, equation 2. So if you look closely, this is something which you already know, the elementary mass equation. That is, it can be written in terms of density into elementary volume, right? Now, once you have these two equations, as you can observe, they actually have three variables here, which are mass, pressure, density. But we actually only have two equations, right? So that means we basically need a third equation. So for that, we bring in the EOS, the equation of state. And yeah, we try to plug it in the first two equations. And from that, we end up with this, two final equations, which have the blue markings. Now, once we solve these two equations, we get ended up with the two solutions, which are the first order differential equations. Now, these equations will be further, integrated, numerically integrated through some computer algorithm, as I have shown here. Now, okay, now for the computer, for it to integrate it, so that is this two first order differential equation, it basically needs two boundary conditions which are in nothing but two initial values. So for that, first it assumes that mass at r is equal to 0 is 0. That is a very basic thing which you can say, right? Now the second thing is we plug in some random central density, some rho c value. So this is what we call as free parameter. Like if we change this density value, then accordingly the central pressure, which we calculate with using the EOS equation, that will also change. But basically, we are changing the initial value, right? So accordingly, this whole process it will end up producing different particular solutions. So yeah, when this computer it repeats this whole integration with various values of central density, we end up with different values of mass and radius. So let's try to ignore radius here. Now that's not important. Now once we take the set of total mass and the some chosen central densities there, and when we try to plot a graph with them, we end up getting this curve which is called this TOV stellar stability curve. Now the peak of this curve is what is represented as TOV limit. So depending on the EOS you take now, this curve, that limit will vary across that limit. So this is not an accurate one. Here I have shown it's some value, but understand this is according to some specific EOS. Now let's try to interpret this graph, how the star behaves here. So for that, first imagine that you are having a neutron star here, a normal neutron star. So in order to undergo collapse to become black hole, it basically has to gain masses, right? And it has to exit the COV limit and all. So for that, let's try to inject some elementary mass and let's try to observe its behavior like second by second. Now, when we talk about it from the stable branch, like when we add the mass, so according to this graph, we have like positive derivative, right? So basically, if we increase the mass, the central density will also increase. So according to EOS, the degeneracy pressure is also increasing here. So this increase in degeneracy pressure, it will balance out that extra gravitational pull caused by the mass added, and that's how they balance out each other and they reach a stable point. And that is why we call this whole branch a stable branch, because whenever a star is here, and when it tries to consume some mass, it will immediately find a balance point. But when it reaches this peak, POV limit, it basically this peak represents the breaking point of the nuclear matter. Right now, the nuclear matter is almost at its maximum limit of fighting against the gravity. So this limit actually tells you how much of a maximum mass a neutron star is capable of holding, before undergoing the gravitational collapse. Now, once ignoring this warning, when we try to go down the descent which we have here on this hill, basically that means we are trying to increase the density, right? So if you see from the graph, the if we increase the density, the total mass which the star is capable of supporting is actually decreasing. You have to understand like how catastrophic this is, because it basically means when this neutron star's density increases, its holding power is dropping below its current weight, meaning now right now it cannot even sustain its own weight. That basically means that gravity will instantly start dominating this quantum pressure. So at some point it will to completely crush this quantum degeneracy pressure which is caused by the neutrons, and right at that moment, the star will start undergoing the collapse and it will collapse past its own RS radius, which is its own event horizon. And thus, it will tear up, the permanent hole in the fabric of space. And all its matter, they will get crushed into a single point of infinite density, which we will call as singularity. And this whole thing will leave us behind. What will leave us behind is a stellar black hole. So right now, I hope how you understood how the black hole forms. So basically, massive stars they become the red supergiants, and then they undergo the core collapse supernova, which will either produce a neutron star or black hole. But if we assume that it produces a black hole, then sorry, if it produces a neutron star, then once it crosses this POV limit, we end up getting this black hole. So this is how the life cycle of massive stars will go on. Okay, now we have got the black hole from them, right? And as you know, they are actually pretty cool and bizarre objects in which we can find in the universe. Why so? It's because basically in front of them, our normal physics they completely break down. So in order to explain how these bizarre objects work, how they bend light or warp the times and all, I will pass the lead on to my friend Gautam. So he will be explaining how this black hole will behave and all. Yeah, thank you.
Thank you, Selvi. Yes, here we go again. Okay, now we have finally reached one of the most interesting parts of our stellar evolution, the birth of a black hole. So yeah, if you look at this, background picture, it almost looks like a giant hole in space that's swallowing everything around it. Actually, it has been taken from a famous movie called Interstellar. I hope some of you guys have watched, and yeah, we shall be seeing few references from that movie. Don't worry if you have not watched the movie. I'm there to explain the context. So yeah, let's get started. Yeah, and that's what most people think a black hole is something like a vacuum cleaner, but that's actually our first misconception. Yeah, black hole isn't really, I mean, it really not a hole in first place. It's an incredibly, dense object formed when gravity gets over a massive dying star. Yeah, let's quickly remember the last session. After the supernova explosion, the outer layers of the star were blown away, but the core survived as a neutron star. And for some time, neutron degeneracy pressure was, strong enough to resist gravity. However, this resistance works only up to a certain limit, which is TOV limit. Yeah, they remain stable only up to the, TOV limit of 2 to 3 solar masses. We saw all of that. Okay, if the remaining core is even more massive, gravity finally becomes so strong. the neutron star, right? It can no longer support its own weight. So what happens is that the core keeps collapsing. It becomes small, denser, and denser. Eventually, it reaches a point where the escape velocity, becomes greater than the speed of light. I mean, imagine that our Earth's escape velocity is 9.2 kilometer per hour. I mean, imagine it to be greater than the speed of light. Yeah, that's how a black hole is born. So yeah, black holes are not some giant cosmic, vacuum cleaners. They don't pull things in. They attract objects for exactly the same reason the Earth attracts us, which is gravity. The only difference is that their gravity is, unimaginably stronger. So yeah, now that we know how a black hole is born, let's see what actually, makes up a black hole. Yes. Okay. What exactly does a black hole look like? It has several important regions surrounding it, and yeah, each one tells us something different. That glowing ring is called the accretion disk. It is not part of the black hole itself. It's made up of hot gas and dust. I know it just spiraling inwards. As it moves faster and faster, the particles collide with each other, and yeah, they became extremely hot. That's why it glows so brightly. So even though the black hole is itself is invisible, the material around it can be incredibly bright, and yeah, still we can see it. Moving a little closer, we reach the photon sphere. Here, gravity is so strong that even light can bend around, as you might have heard. Next comes the most famous spot of a black hole, the event horizon. You have probably heard it called the point of no return. That's exactly what it is. Yeah, it isn't a solid surface. It's simply an invisible boundary. And yeah, once anything crosses this boundary, not even light can escape. So yeah, and finally at the very center, what we have is the singularity. Yeah, according to our current understanding, this is where matter is compressed into an extremely tiny region. But this is also where our present laws of physics stops. So the singularity remains one of the greatest mysteries in modern science. Okay, so summing all things, we have seen the glowing accretion disk, the photon sphere where light bends, the event horizon, which is called the point of no return, and finally the mysterious singularity at the center. Yeah, but this brings us with another interesting question. How can a black hole, really bend even light? To answer that, we need to understand Einstein's idea of gravity. Now, here's something that might sound a little strange. We often say that black holes have an extremely strong gravitational pull, but according to Einstein, gravity is not really a force pulling objects. It's actually the bending of space and time itself. So, if you look at this picture, imagine this gray sheet represents space and time. Whenever you place something, with mass on it, the sheet bends. The bigger the mass, the deeper the bend. I mean, as you could see. So a planet like the Earth creates a small curve. Our sun creates a much deeper one. But a black hole is, as you could see, is on a completely different level. It bends space and time so much that even light is forced to follow that curve. That's why light appears to bend around a black hole. So black holes don't pull light like they pull, I mean, something like a vacuum cleaner and all. They simply bend the space through which the light is also traveling, and light has no choice but to follow that curved path. And here's something even more interesting is that if space is affected by gravity, then yeah, time should be also affected, right? And yeah, that's exactly what Einstein predicted. So now let's see what happens to time itself when you go near a black hole. All right, we'll explain about this picture in a while. Okay, what happens to time near a black hole? To understand that, we need to look at two of Einstein's greatest ideas. The first one is special relativity, and the second is general relativity. I'll explain it simply. Special relativity tells us that when something moves at speeds closer to the speed of light, time begins to slow down. It sounds unbelievable, but yeah, it has been tested and confirmed. General relativity tells us something equally fascinating. It says that gravity also affects the flow of time. So the stronger the gravitational field, the more slowly time passes. Now, okay, imagine you are standing near a black hole. I mean, you won't feel anything unusual. Your watch will tick normally. Your heartbeat will be completely fine. Everything around you will be, seem absolutely fine. But if something is, sorry, if someone is watching all this from far away, they will see something completely different. For them, your clock appears to run slower and slower. And the closer you get to the black hole, the greater this, difference becomes. I mean, it's very hard to understand. That's actually the idea shown in the movie Interstellar. The context is that on one of the planets near a black hole, just 1 hour passes, while about 7 year passes here back on Earth. Although the exact numbers in the movie depend a lot on the particular black hole, the science behind the idea comes directly from our Einstein's theory. Black holes not just change space, but also the time itself. And yeah, I think it's one of the reasons black holes continue to amaze scientists even today. But here's another interesting question. If black holes trap, almost everything that comes near them, is there any way by which we can actually extract energy from one? And surprisingly, the answer is yes. Let's see how it is done. Okay. The process is something called Penrose process. So far, we have been looking at black holes as objects that trap everything around them. So yes, an interesting question. Can we ever get something back from a black hole? I mean, it may sound impossible, but yeah, before we answer that, there's one important thing to remember. Not all black holes are the same. There are two types of black hole. I mean, yeah, yes, there are many types, but based on its motion, there are two types. One is stationary and other is rotating. So if a black hole is spinning, something very interesting can happen. The idea is called Penrose process. It is just a theoretical method of extracting energy from a black hole. Okay, if you look at this figure, you will notice a region just outside the event horizon. This is called the ergosphere. Unlike the event horizon, it's still possible to escape from this region. But because the black hole is rotating, it drags space and time along with it. So anything entering this region is supposed to move around the black hole. Now imagine a particle entering the ergosphere. It splits into two smaller particles. One falls into the black hole, and while the other escapes. And is the interesting part, this escaping particle, right? It comes out with more energy than the original particle. So where did that extra energy come from? It actually comes from the black hole's rotation. So yeah, in this way, black hole gives up its small amount of rotational energy. That's why the Penrose process is, considered a theoretical way of, extracting energy from a spinning black hole. I mean, it's a quite interesting theory. So yes, if a single black hole can produce such fascinating effects, what happens when two black holes come together? Let's find it out. Okay. So far, we have been talking about a single black hole, but our universe is far more vast and wide. So yeah, many black holes exist in binary system. If you look at this picture, that's exactly what's happening here. Both black holes are moving around each other because of their what to say enormous gravitational attraction, but they don't keep orbiting forever. With every orbit, they lose a tiny amount of energy. As a result, they slowly spiral closer and closer together. and eventually it reaches a point where they collide and merge into a single but also larger black hole. This entire process happens in just a fraction of a second. But in the short moment, a massive amount of energy will be released. In fact, the merger can release more power than all the stars in the universe combined. Yeah, and it's most important to note here that energy is not released in the form of light. I mean, this collision releases more amount of energy as something called gravitational waves. So yeah, after the collision, what remains is one larger black hole, but the story doesn't end there. The collision sends tiny ripples across the entire space-time fabric, and these ripples even travel across the universe at the speed of light. So yeah, what exactly are these gravitational waves? I mean, these ripples. And actually, we have detected some of its signal. And yeah, how did we detect something so, small, something so small? Let's look at that next. All right. So in the last slide, we saw two black holes spiraling towards each other and finally merging into one. But I also mentioned that this collision sends ripples through space-time. Yes, this is what we call gravitational waves, as you could see in the animation. They travel across the universe at speed of light. Now, here's the amazing part. By the time these waves reach Earth, right, they have become very, what to say, very tiny. Imagine trying to measure something that small. I mean, it may sound almost impossible, but scientists did it exactly that using an observatory called LIGO. Instead of looking for light, they listen for this, tiny distortions in space-time using laser beams. In 2015, for the very first time, we detected gravitational waves produced by these mergers. This discovery was so important that it, earned 2017 Nobel Prize in Physics. So today we don't just, we can not only observe the universe with telescopes, but we can also hear, or listen to some of the most violent events which is happening billions of light years away. But this brings us to one final mystery. So far, we have seen black holes, pulling matter inward. But can a black hole ever lose mass instead of gaining it? This is also another means of black hole shedding its own energy. Surprisingly, one physicist believed that answer was yes, yes, it can shed its own energy. And yeah, who do you think it is? Who comes to our mind while talking about black holes? Yes, it's our legend Stephen Hawking. Let's see what he proposed. So, okay, so far we have been thinking of black holes as objects, that only absorb matter and energy. So it seemed natural to assume that once a black hole is formed, it can only keep growing. But yeah, that changed in 1974. Stephen Hawking he proposed something truly interesting. He suggested that black holes are not completely black after all. They can actually emit a tiny amount of energy. And yeah, this phenomenon is what we call Hawking radiation. Now, see the picture here. This is not a COVID-19 virus. I mean, it's a black hole emitting Hawking radiations. Now, this doesn't happen because light escapes from inside the black hole. Remember, once something crosses the event horizon, it still cannot come back. Instead, Hawking radiation is believed to occur just outside the event horizon. You can think of it as the black hole, slowly leaking away a tiny amount of its energy. This radiation arises from quantum effects near the event horizon, you can say. This means that every time Hawking radiation is emitted, the black hole loses an extremely small amount of its mass. But yeah, don't worry. For the black holes we know today, this process is very slow. In fact, a stellar mass black hole would take far longer than the current age of our universe to completely evaporate. So yeah, this isn't something we will ever witness happening in real time, but it completely changed the way, we thought about black holes. Yeah, instead of being eternal, black holes may eventually disappear. So black holes begin with the collapse of a massive star. They spin space and time. They can merge with one another, and yeah, according to Hawking, they may even slowly fade away. So yes, with that in mind, let's conclude our journey through one of the most stunning objects in your universe. Okay. Okay. So far, we have explored how black holes are formed. We understood their anatomy. We seen how they, bend space and time, and we have even discussed how they can merge and slowly, lose mass through Hawking radiation. But here's the question: if black holes don't emit light, how do we know they do even exist? I mean, for a long time, black holes were only mathematical predictions. Scientists believe they existed, but yeah, no one had ever actually seen one. That changed in 2019 when scientists released the world's first image of a black hole. Yeah, this is M87. It's a supermassive black hole. It's located at the center of the galaxy called Messier 87. Now, here's something very important to remember is this isn't a photograph of the black hole itself because the black hole is completely dark. What we're actually seeing is the bright glowing material in the accretion disk surrounding it. The dark region at the center is the shadow created by the black hole. I mean, capturing this image wasn't very easy. Scientists combine observations from, various radio telescope across the world. And yeah, after years of collecting and processing data, we could finally produce this historic image. Actually, it transformed black holes from yeah something we could only imagine into something we could actually observe. So yeah, from the birth of stars to the mysteries of black hole, we have traveled across one of the most interesting journeys in our universe. So yeah, I guess we can wrap it all up. Yep, we won. Ever since the beginning of civilization, human beings, we have always looked up at the night sky with, wonder. We have always asked the questions, what are those stars? How did the universe begin? Are we alone? And yeah, what lies beyond, what we cannot see? And even today, the universe continues to, inspire us. Black holes, dark matter, dark energy, even the origin of the universe itself. There is still so much left to discover. But yeah, despite all those mysteries, we learned how stars are born, we understood how they live, we discovered how they die. We predicted black holes long before we ever saw one. But yeah, today we can even detect ripples in space time and capture images of objects that were once thought to be impossible to observe. Because every discovery we have talked about today started with someone asking a very simple question: why? I mean, it's very important. Why not in this way? Why in this way? Why not in the other way? I mean, the word why is really important. So, yeah, the real objective of this session wasn't just to explain astronomy, it was to, ignite your curiosity about the universe. Because who knows, the next person to answer one of the universe greatest mysteries might be someone listening to this session today. So yeah, the stars may have reached the end, but summer school is just getting started. Don't miss our next session on 14th July at 5 p.m., where we will be exploring nuclear fission and nuclear fusion. I mean, we will be looking deep inside the stars. So yes, thus we reach the end of stellar evolution. Thank you, everyone. And yeah, before finishing, I want all of you guys to scan this QR. And yeah, this is attendance form. And yeah, uh, give us your valuable feedback. Thank you, everyone, for joining us today. I hope you all have a good day. And yeah, keep looking up. Thank you. And yeah, you can also, take screenshot of this and yeah, start filling out it.